Hey everyone, welcome to this Ultimate Classroom Review Session Explainer. If you're getting ready to master the science of heat and temperature, you are in the exact right place. I'm absolutely thrilled to be your guide today. We're going to take all those tricky concepts from your textbook and break them down so you can completely ace your next test. So grab your notebooks, get comfortable, and let's get ready to learn. All right, here's our agenda for today's review. We'll hit Intro and History, Thermometers and Safety, the 3 heat transfers, nature's breezes, colors and heat, and then wrap it all up with a pop quiz.
Okay, let's dive straight into Section 1, Intro and History. So I want you to think about this for a second. How do we really know if something is hot? I mean, your first instinct is probably, well, I just touch it, right? But honestly, our sense of touch is kind of easily fooled. If you stick one hand in cold water and the other in hot water, and then plunge them both into a bowl of room temperature water, your hands will be completely confused. One hand will literally feel hot and the other will feel cold, even though they're in the exact same water. Because our hands can be tricked like that, scientists need a much more reliable measure, and that measure is what we call temperature.
Now check out this wild bit of scientific history. Before the scales we use today, Gabriel Fahrenheit developed the early Fahrenheit scale. But when the Swedish astronomer Anders Celsius devised his own scale in 1742, he originally made it backwards. He actually fixed the temperature of boiling water at 0 degrees and freezing water at a blistering 100 degrees. No way, right? Thankfully, scientists realized that was incredibly confusing, and the whole thing was reversed very soon after.
Moving right along to Section 2, Thermometers and Safety.
So, we've got 2 main types of thermometers you really need to know. First is the clinical thermometer. This one is strictly for human bodies. Because our body temperature doesn't actually vary that much, its range is only from 35 degrees to 42 degrees Celsius, and it features this special little bend called a kink. Then you have the laboratory thermometer. This is your go-to general science experiment tool. It has a much wider range, usually from -10 degrees all the way up to 110 degrees Celsius, and it does not have a kink.
So how do we actually use these things? Well, inside traditional glass thermometers, there's a liquid metal. You literally just rotate the glass until you catch that shiny thread of mercury. As things heat up, that thread expands and climbs up the numbers. In a clinical thermometer, that little kink near the bulb is a real game changer. It stops the mercury from falling on its own once you take it out of your mouth, giving you plenty of time to read it. But hey, safety first. Mercury is a highly toxic substance. If a thermometer breaks, it is extremely dangerous. Also, never ever put a clinical thermometer near a hot flame or in boiling water, or it'll shatter.
All right, here is the big one. Section 3, the 3 heat transfers.
Let's get into the rules of how heat actually moves, because heat always flows from hotter to colder. First up is conduction. This is the process where heat transfers from the hotter end to the colder end of an object, and this generally happens in solids. Imagine you have a flat metal strip, like aluminum or iron, and you stick little pieces of wax to it. If you heat one end with a candle, the heat slowly travels down the metal, melting those wax pieces one by one. That direct particle-to-particle transfer through a solid, that's conduction.
Next is convection. Water and air are actually pretty terrible conductors of heats, so they have to use convection instead. This is the mode of heat transfer in liquids and gases where the hot fluid gets lighter and rises, and the colder fluid rushes down from the sides to take its place. It's all about this circular motion. Heat a pot of water, the bottom gets hot and goes up, the cold water at the top rushes down to the bottom to get heated. It's just a continuous rolling cycle.
And our third method is radiation. This is the ultimate space traveler of heat. It's the transfer of heat that does not require any physical medium at all. No solids, no liquids, no gases. It can literally travel through the absolute vacuum of space. This is exactly how the immense heat from the sun manages to reach us here on Earth, traveling millions of miles through empty space just to warm your face on a sunny day.
And this brilliantly illustrates how these aren't just invisible rules. Let's look at Section 4, Nature's Heat, the Breezes.
First, let's talk about a really cool lab experiment. To actually see convection in water, scientists will drop a pink crystal of potassium permanganate into a flask and heat it from below. Just like we talked about, you can physically see the colored streaks of hot water rising straight up from the flame, while the cooler, heavier water rushes down the sides to replace it. It creates this awesome, visible, rolling pink current. Now imagine that exact same circular current, but the size of an entire coastline. During the day, land heats up way faster than ocean water. The air above the land gets hot and rises, and the cooler air from the sea rushes in to fill that space. That's why you feel that super refreshing sea breeze during the day. But at night, the whole thing flips. The land cools down incredibly fast, but the ocean holds on to its heat. So the air over the water rises, and the cool air from the land rushes out to sea, creating a land breeze. It's literally just giant-scale convection.
Okay, moving on to Section 5, Colors and Heat Absorption.
Believe it or not, understanding heat radiation is the secret to dressing comfortably for the seasons. Think about this simple tin can experiment. You take two identical containers, but paint one completely black and the other bright white. If you pour the exact same amount of hot water into both at the exact same temperature and leave them in the shade for a bit, something magical happens. When you check the temperature again, the water in the black can will have cooled down totally differently than the white can.
So here's the big scientific takeaway. Dark surfaces absorb a whole lot more heat, but they also radiate it away differently. When you're out in the sun, dark colors soak up that radiant heat like a sponge, making them absolutely perfect to keep you cozy in your winter clothes. Light colors, on the other hand, act like mirrors. They reflect most of the radiant heat that hits them. That's exactly why light-colored clothes are your best friend in the summer, keeping that solar radiation far away from your body.
All right, you guys are doing incredibly well. It is time for Section 6, Review Time, Pop Quiz.
Let's jump right into it. Here's your first question. Fill in the blank. Heat is transferred in liquids by the process of what? I'll give you a second. Picture that boiling pot of water.
It's convection. Yep, remember liquids and gases use that rolling circular motion where the hot fluid rises and the cold fluid sinks? Awesome job if you got that.
Question number 2. Fill in the blank. No medium is required for transfer of heat by the process of what? Think about the sun, millions of miles away in empty space.
Radiation, it's the ultimate space traveler. It doesn't need any solids, liquids, or gases to move energy around.
Okay, final question. Imagine this. A cold, solid steel spoon is dipped into a steaming cup of hot milk. Heat is transferred up the spoon to its other end by the process of what?
Conduction. Because that spoon is a solid metal, it conducts the heat directly up into your hand. You all did a fantastic job reviewing today. But hey, before we wrap up this explainer, I've got a final provocative thought for you to chew on. We learned that trapped air is actually a really poor conductor of heat, right? I mean, that's why fluffy wool sweaters keep us warm in winter, by trapping air against our bodies. So if trapped air is such an amazing insulator, could we revolutionize the way we build our houses? Could we use hollow bricks, literally bricks filled with trapped air, to insulate our homes and keep them perfectly cool in the summer and warm in the winter? Just like a giant wool sweater? Think about that. Thanks so much for joining me today. Keep asking great questions, and I'll catch you in the next explainer.